All right, recording is rolling. It is Wednesday, May 15th, 2 days until the AP exam, which of course is at 7:30 in the morning in the gym. So for context, over the past couple weeks, how the schedule's panned out is each class had a different amount of review time. So period 6, all right, ask you guys right before I hit record what you guys want to do. And I think we're going to do is go over to this grid page and then got some extra time, we'll flip over to AP Classroom. So I think that's our plan here. Okay. All right, so here we go. You guys might have this page. I got about 5 or 10 extra copies right here. They put up right here if somebody wants to pick up one, but I just gave you guys an extra copy this week. All right, so here we got the units, unit 1, unit 2, unit 3, 4, 5, 6, and then if you flip it over, I got unit 7, right? 8, 9, and 10 have been removed. Back in 2019, they used to ask. Pandemic rolled around and they bumped these and they've not returned everything. And then down at the very bottom, got vectors of trigonometry, prefixes, some reference, some basic graphs. Okay, so you got that, right? Right. So the middle of the backside, you can ignore those rows, but everything else is good enough. Right, and then going across. Okay, so I have some bullet points within each unit. Just very briefly, what are the main topics? Right. So kinematic motion, linear and projectiles. There you go. That pretty much covers kinematic, right? Right. Key flag. A lot of students have asked me over the years, like, how do I know if I get, just some random MCQ question, like what framework to think of it in terms of? Like, how do I know to, solve using forces versus energy versus momentum, right? So okay, yeah, that's a good question. So I tried to give some hints as to, what would key you in as to, okay, I'm going to do like conservation momentum because I see a collision, right? Right. Some main formulas. All right, try to squeeze all the formulas I thought you guys might need here. Right, there's a couple extra ones too. Right, some classic examples. I try to pick at least a couple of classic examples that like go to. Okay, you're gonna get. You're gonna get inclines. You're gonna get outwards. You're gonna right. It's gonna happen, right? And then some classic graphs. You see graphs all over the place. So properties graph. These aren't all the graphs you'll see, but here's like some main ones you gotta know. At least, right? So yeah, there's the organizations page. Right, now let's dive into this. So start with kinematic motion, and then I'll just go across the row here. Right. So yeah. So you could be going forwards or backwards on a say straight track. Sometimes say that like there's a car going on a straight track, right? Maybe it's in reverse, maybe it's forward, right? It could be a graphical situation. You got two cars you're comparing the graph, right? And projectiles is the other main category, right? So you guys know you throw something through the air at some angle. See, gravity is always pulling down. It's accelerating only down, right? But its horizontal motion is constant velocity going across the field, just like that, right? And so there's the big picture concepts. If you can identify 3 kinematic variables, right? And there's these 5 that we're juggling. So time, acceleration, displacement, initial velocity, final velocity. If you can identify 3 of those, then in principle, you can solve the other 2 with these kinematic formulas right here. Boom, these 3 guys, right? Sometimes they'll say something like something's dropped or starts from rest. Say, oh, that means initial velocity 0. Sometimes they say like a car brakes to a stop. That means final velocity 0. So even though it's not an explicit number there, right, there's something about here. Sometimes Earth gravity field is implied, right? You drop a ball off a cliff so high or something, right? But maybe they won't tell you 10 meters per second squared Earth gravity. So, okay, well, I can kind of assume I'm probably on Earth for this route, right? Unless they specify otherwise, right? You guys got that? Right? So here's 3 kinematic formulas. A lot of times these simplify. For example, if it's a non-accelerating situation, then all of these just condense down to this: distance equals b times time. That's it, right? X equals dt, right? If a is equal to 0, then that's all it boils down to, right? If you start from rest, say if you drop a ball from the edge of a tower, then v naught goes to 0, and then again we simplify a little bit. Okay, right? So a lot of times that. Classic examples. We got a couple examples here. A ball is dropped from a cliff of known height on Earth. Okay, right there. There's already 3 kinematic variables, right? Dropped, initial velocity 0. Known height, right? The vertical displacement. On Earth, the gravity field. Boom, boom, boom. There's 3 kinematic variables, right? How fast it will be moving when it hits the ground. So you're solving for final velocity. You could use that one right there. Guys, what's the other question they could have asked? Yeah, how much time, right? How much time, right? Now that's if you're solving for something. You guys know AP likes proportional questions too. So, how about this? What if you have a cliff that's 4 times as tall? Right, so you got 2 cliffs. You got the regular cliff, and you got the 4 times as tall cliff, right? How do the crash speeds compare? So the short cliff, there's some speed. So the tall cliff, what's the crash speed compared to the short cliff? If it's 4 times the height, that's a factor of 4 in that x. You're solving for final velocity. 2 times, because you take the square root. Guys see, right, dropped means v not goes to 0, just ignore that. Right? You square both sides. V equals, hey, square root 2ax. It's like square root 2gh, isn't it? It's the same thing. Right, guess it. Right. So the proportion question. What's the other one I got here? Ball thrown horizontally from the edge of a cliff of known height. That sounds like a projectile. Right? Where will it land? Right? So, 2 parts. You got to break this down. What's going on vertical? What's going on horizontal? And depending on what information you have, the projectile, right, you might start with one or the other information. Right? So here we go. So if you know the height of the cliff and you blast this horizontal, right, that means that the time to fall, you can use y equals 1/2 dt squared. Right, so you can solve for time. There we go. Solve for time to fall. Right, and then you can take that time and flip over to x equals vt to figure out horizontally how far it goes in that time. Right? You know how fast you blast it. Right, guys figure that? Right. I think the poster I made of this is kind of the reverse question of that. I said if you know the height of the cliff and you know where the ball lands, can you back calculate the blast speed? Right, it's just kind of this in reverse. Right, you go about both ways with that. Right. Right. Classic graphs. Right, guys. V versus T graph. You know you're going to see multiple of these, right? You're going to see multiple of these. I'm curious how many of those you're going to get. Maybe 3, 4, 5. And lots of properties this has. So the slope is V versus T is acceleration. The area under the curve is displacement. Lots of graphs you're going to see with lots of properties. What's the slope? What's the area? If you're ever not sure, then look at the units of the variables on the axes, like velocity, meters per second, time in seconds. So if you divide those two, guys, what is meters per second divided by seconds? Meters per second squared, which describes an acceleration, right? And then slope is rise over run. Okay, so the slope is acceleration, right? And then what if you multiply it? What is meters per second multiplied by seconds? What is that? Meters. Okay, which describes the displacement, right? Which has, hey, isn't that something to do with areas like base times height, right? Right. And a triangle is like half base height. Right? Okay, you guys see how the units and the properties of the graph go hand in hand, right? Now that's just for that graph, but it could be. All right, here's all right, I got a couple of projectile sets over here. Right. Let's say you blast you guys remember in the lab, we took the launchers to the balcony and blast them horizontal and watch bam, like where do they land? You guys remember that? You guys actually calculated the blast speed, right? There's a poster I made for that too, right? Where does it land? What's the height of the cliff? Calculate that. Here's the graphs to go along with that scenario, right? So X for well, maybe if I made this Y versus T, right? That could be maybe the vertical velocity, right? Okay, so this could be its vertical component velocity. So it's accelerating in the vertical direction, right? It's picking up speed at a constant rate, and it has constant acceleration like that, right? If you, or actually, I didn't look at these before I said what this was, right? Actually, these are different scenarios. Now that I'm looking at these are different scenarios, right? It could still be vertical, right? But here's a completely different scenario. Guys, what could be going on with this graph? It's a set of graphs on the right. I got a set of graphs. What's one thing that could be going on? What's a story you could catch that? How about this? How about down is positive? See, it's tending towards down, right? You've got a free fall scenario, right? And you throw the ball straight up, right? So you're on top of a balcony. You throw the ball straight up, right? It goes, reaches its maximum height here, and then comes back down, and then misses the balcony, keeps falling back down to the valley below, right? Could be that, right? So those would go hand in hand, right? These are the same acceleration, right? So whether you drop the ball or if you throw it upward, right? Once it leaves your hands, free fall, gravity. Right? That's it. Right, so you guys pretty set with kinematic motion? You guys got? All right, let's do unit 2, dynamics. So forces, Newton's laws. If there's an equilibrium question, maybe I should throw that as a bullet point here. Equilibrium. Right? Actually, it's more of a key flag, isn't it? Right. So you guys know Newton's laws of motion, law of inertia, Newton's second law of motion, A equals F over m, equal and opposite forces. Boom, boom, boom. Right, you guys know those? Right, when two objects are pushing or pulling on each other, equal and opposite forces. Right. So for equilibrium, you guys know the sum of forces goes to 0 newtons. That could be true in each direction. You could introduce a coordinate system that break it into x and y components, right? That would still be true. And then therefore there would be 0 acceleration, 0 force, 0 acceleration go hand in hand. It's like Newton's second law of motion, right? Oh, not necessarily 0 velocity. Now, if you're just sitting there at rest, that is also equilibrium, right? But guys, what if you're in a plane going constant velocity through the sky? Is that also equilibrium? Yep. Constant velocity is an example of 0 acceleration, zero net force, right? There can be forces, they just all zero out. Okay. So like the thrust force and the drag force on the plane are zeroing out. Ooh, here's Newton's second law. You're going to use that. Ooh, friction force is coefficient of friction times normal force. Now, if it's kinetic friction, then you can say equals. If it's static friction, it builds up to that possibly. Right? Guess what? So throwing in inequality. Oh, tension in an elevator cable. Look at this. M times G plus or minus A. I think that's a good one to be able to pull out of your back pocket to solve a multiple choice question real fast. If it's a free response question, they will expect you to derive that from scratch, but we've gone over that. You guys have a poster on that, right? You can derive that from scratch, right? Ooh, Hooke's law, F equals kx for a spring. Don't mix that up with energy in a spring, which is 1/2 kx squared. So if it's spring forces, F equals kx. The spring energy, that's a different unit, 1/2 kx squared, okay? And then here we go, equilibrium, zero net force. And also zero torque, which is actually a unit 7 concept, but you guys know that by now too, right? Right. This incline, guys, you know you're going to get some incline questions, right? And I had you guys do this in the notes the other day. I said, draw a block on an incline, draw the free body diagram for equilibrium, right? So you got to be able to draw this. So here, the weight force pulls straight down, so you draw an arrow straight down because we're going to pull straight down. Right? Label that mg or f sub g, right? But you got to label it, right? If they want to have a free body diagram, you got to label the forces. Okay? I got the normal force up at some angle, and I got the friction force resisting the motion. So that could be equilibrium. That could be, right? Right, classic, right? This angle is this angle. Normal force is mg cosine theta, right? And if it's true equilibrium, then this friction force would be mg sine theta, right? Right, guys got that? Okay. You know you're going to see some Atwoods, right? Lots of questions that get asked about Atwoods. Right? Physics 1, love Atwoods, right? So got mismatched masses and weights. See, the large one's going to fall down, the small one's going to pull up. Right? And then there's some tension in the string, which is like a medium-sized force. It's larger than the small weight, but it's smaller than the large weight. So they can, right? So they can have opposite motion, right? Get that? You could be asked, what's the acceleration? And they would usually phrase it, what's the downward acceleration of the large mass? Right? You could be asked something about the tension. I wouldn't be surprised if AP like swaps out the masses and has you compare different tensions and different Atwoods, right? So be ready to put something like that. Right? If you have to solve something exactly, you could put some numbers down and compare your numbers. Like, oh yeah, that number is bigger than that number, and then get the right answer anyway. They could ask, let's see, how fast is it moving after some time interval? Right? That's dynamics and kinematic, right? They could ask, how fast is it moving after some distance move? That could also be dynamics followed by kinematics, but alternatively, you could do conservation of energy for that question specifically, right? How fast is it moving after some distance move, right? Conservation of energy, right? Right. We've been setting those up the last few days, guys remember, right? If you need to review any of this, we've gone over posters the last few days, so there's a poster for each one of these scenarios. All right, so got that. I don't want to shuffle back and forth because I just want to kind of stick to this right now, but back to your notes, we've gone over all this. All right. Did I make up some kind of random tech graphs here? Yeah, great. Because every once in a while, AP will throw you like a complete curveball graph. Like, I've never really seen this before, right? But you can look at the units, you can figure out what's going on with it and what properties are what. So if you got, what's this? Friction force versus normal force. Say you're dragging objects across the surface or something, right? Right. And see, the more the normal force, the more the friction force from the same materials. Oh, well, I know friction force is coefficient of friction times normal force. Hey, that sounds like y equals mx. Ah, that means that the slope of this line represents the coefficient of friction for that particular context. Okay, right, right. What else do I have here? Force versus distance. Ooh, for compressing or stretching a spring. Hey, does that look like Hooke's law? Right, Hooke's law, right? Right. And the area could be the energy stored in the spring or the work done stretching or compressing the spring, which of course be the same thing. Right? You guys got that? Pretty good so far? Right, so that's all my examples on the page for unit 2. Right, guys ready for unit 3? Right, so remember this was a hodgepodge here. We got centripetal force, circular motion. Right, there's also universal gravitation. You can put all that together and make orbits. Isn't that unit 3? So let's check this out. What's the force holding something in circular motion? So centripetal force, gravitational attraction. See orbits. Don't worry about it. They're not going to ask that. Right. Okay. So all right, you got centripetal forces mv squared over r. I don't think AP Physics goes too much into m omega squared times r, but I think that's good to know, right? It might help you out a bit, right? Here's universal gravity force, gmm on r squared. Here's gravity field, gm on r squared, right? Just divide through by the mass being accelerated, right? Got gravity field, right? Don't worry about universal potential energy. AP's not going to ask that, right? Ooh, speed for a circular orbit, square root gm on r. You probably have that memorized by now. If that's a free response question, they'll expect you to derive that from scratch, which we've done a lot of times in this class. Can you guys derive orbital speed from scratch? Hopefully, right? You guys see that? Right. And guys, this r over and over and over, this r represents the distance from the object to where? To the center of the planet, right? Center of the planet, right? If you were walking around on the surface of the planet, that also happens to be the radius of the planet. You guys see that? Okay. Right. Oh, and then I gave you guys universal gravity constant right here. I think AP also gives that to you, don't they? Yeah, they do. All right. So here's the page I usually refer to. Right. A bunch of these equations are also on here. Right. If you flip over to the other side, they do give you some constant. Here's your universal gravity constant right here. Okay. So they give you some. Right. Here's some prefixes, trig function, ratios. Got all that. Right. What's next here? Ooh, I got a whole list of examples. It's like 7 examples. Let me zoom in where you can read these. Right. What's the tension that holds a ball on a string in a circle? Right. You guys did a lab with that. That's how you guys derive centripetal force. Right. If you assume it's a horizontal circle or a pretty flat circle, you just do mv squared over r. If it's a conical pendulum, you got to consider, or if it's a very pronounced conical pendulum. Okay, well, there's we look at a poster for that too, right? There's a vertical component and a horizontal component to the tension, right? The string, right? How does centripetal force relate to mass, speed, and radius of curvature? Oh, F equals mv squared over r. You guys got that? Or it could be a friction force holding a coin on a turntable, right? Usually easier to solve with omega squared times r, m omega squared r, but you could go to what's the you could do mv squared over r. Frame it that way. What's the minimum speed for a roller coaster to complete a loop given the radius of the loop in the gravity field? Right. So here, got a vertical loop. The roller coaster's going around. You could tell me, in terms of the radius of the loop, what is the minimum speed to get around the top? Square root gr. Right. You guys remember that? Right. And you could solve that with force equilibrium. Well, you say mv squared over r is just equal to mg, right? Because the normal force on the track would go to 0. So that's how you prove that, you derive that. Okay. How do gravity force and gravity field relate to, mass and size of a planet? Did we do some examples like that the last few days? Is if you scale up, there's some planet that's like 3 times the mass of Earth and 2 times the radius of Earth. What's the gravity field at the surface, right? I just made a new poster, showed you guys both the answer to that question and also the density of this other planet, right? Okay. So it's like a scaling question, right? You guys were looking at that the other day? Okay. Yeah, we've gone over examples for that last couple of days. We did that. What's the if you, by the way, if you were taking an AP exam, possibly when we were going over the reviews to these specific questions, you guys know I've uploaded the videos from last few days. So go back and watch the videos from any class that you may have missed over the last couple of days from taking AP exams. Right? You'll see all these here. Orbital speed for a satellite in circular orbit. Okay, there's your square root gm on r. Right, and be ready to derive that from scratch. Right, escapes. Oh, actually, let's skip escape speed. But you're not going to be asked that. Right. Linearization. So, extremely likely chance that you're going to be asked to linearize graphs. Right. That's going to show up on the exam. How do you linearize graph? Right. A good example here. Suppose centripetal force could be mv squared over r. Right, and you get a data table. You get different forces and different radius and different speeds and like a whole table stuff, right? And maybe the question, this would be a weird question, but it could come up, right? Is what's the mass of the ball that is associated with all this, right? So you see the same mass over. So you got that experiment you guys did where you were like wheeling the ball around on the string, right? And you're trying out different speed, different radius and different speeds. So you're changing the radius and changing the speed, and there's different forces resulting, right? But you're using the same mass over and over and over again, right? How can you figure that out, right? Well, you can rewrite. This is just one way to do it, not the only way. Here's one way. I could cross multiply that r and do f times r. I can put that on the y-axis, f times r, right? I could keep v squared on the x-axis, right? Now that's manipulated, right? Because you got v, and then you have to square that, right? And maybe you have like 5 different points, and they'll all line up on a straight line, and that slope would represent mass. Here's how you know. F times r equals mass times v squared, right? Because that's just f equals mv squared over r, just rearranged, right? It's the same thing, right? So you're going to have to linearize something. I don't know what you're going to linearize, right? It might be that right there, right? It might be something different, but you're going to have to linearize something. So you guys can linearize. So take some formula, can you rearrange it to somehow get it in the form y equals mx, right? So f times r could be y, b squared could be x, and then in this case, the mass is the slope, right? Y equals mx. Right? This one's fun. Right? What's your weight relative to a planet, any location relative? So if you're at the center of a planet, you're floating around like an astronaut. Right? If you're on the surface of the planet, you definitely have some weight. You can prove that there's a linear relationship going down, like journeying to the center of the Earth, right? As long as you assume uniform density of the planet. Right? And if you take off in a rocket ship, it tapers off 1 over the distance squared. Right? So there's a big picture there. Right, you guys good? Okay. Couple graph examples. You guys ready for energy? Unit 4, energy. Let's take a look. Okay, so conservation of energy, open and closed systems. Remember, energy is a scalar value. If I, maybe I should add to this list is something like, if you see something maximized, like maximum string stretch, versus equilibrium spring stretch, right? Like, the spring stretching, is it equilibrium? Is it maximum? Because equilibrium is back to like unit 2 with Hooke's law, F equals kx. Maximum spring stretch, probably want to use 1/2 kx squared. Okay, right, something like that. So see if objects are changing height, because that could be changing gravitational potential energy. Changing speed, that could be changing kinetic energy. Being pushed around, there's work being done, force times distance. If there's a spring involved, 1/2 kx squared, possibly, not necessarily, but maybe, right? There's other spring questions too, but it might be an energy question. Hit 2 relevant points, set up a conservation equation. Okay. Here's okay, closed system, energy at point A is equal to energy at point B, or the sum of energy. If it's an open system, you could have plus or minus work. Right? Like okay, I got a couple examples lined up for each of those. Okay? Remember, work is force times distance. That's a dot product. Potential energy, mgh. Don't worry about the universal one. They're not going to ask that. Spring energy, 1/2 kx squared. Kinetic energy, 1/2 mv squared. Maybe know this one too. Rotational kinetic energy, 1/2 I omega squared. And you might get a power question. Power is rate of energy transfer. That's called work over time, right? And for an elevator, say being pulled up by a cable, could that be also force times velocity? Right. Showed you guys the other day. It's real. Okay. You guys want to? Okay. All right. So here's a closed system example and an open system example. Hey, look who it is. This one right here. You guys remember this one? Pushed against a spring, let go, flies around. Right. Suppose there's negligible friction on the surface, right? So all the energy was in the spring. That's 1/2 kx squared. Suppose there was like 100 joules, right? And then maybe the question could be like, how fast is it going at the top? So you like go, right? Well, some of the energy went to lifting against gravity, so that's mgh, potential energy, okay? And whatever's left over is in a kinetic. Okay. So maybe it was 100 joules to start out with, and it took 70 joules to get to the top, and you have 30 joules left over for 1/2 mv squared, right? And then if you know the mass of the object, you can solve for v. Okay, you guys got that? Give some numbers, you can plug in. Right? Open system, classic example, car brakes to a stop. So it started out with all 1/2 mv squared, subtract off friction force times distance, and it was 0 joules at the stop point. Right. And then a little bit more you can do with that. Yeah, there's a poster for that I started with that exact scenario and then derived braking distance as a function of initial speed of the car. Right. Okay. Here, let's see how many guys remember this. Right. So here's a question that goes hand in hand with that example. Suppose you have a car, right, and it brakes to stop, like so many meters, right? And you got another car. Let's say this new car is 3 times the mass, and everything else identical. Same initial speed, same tire, same roof. Right? Okay, so the 3 times mass car has what type braking distance compared to the original car? The same. Yeah, the mass ends up canceling out, right? What about if there's a car with 3 times the initial speed? 3 times the initial speed has how many times the braking distance? 9 times. It's 9 times the energy. Yeah, 9 times. Okay, you guys remember that? Okay. What if it's 3 times the mass and 3 times the speed? Yeah, the mass doesn't matter, but it's just still be 9 times, right? Oh, you're gonna see this graph. Force versus distance. The area under that graph is work, right? The poster version I made was a constant force. Here I'm showing like a triangle-looking shape, right? But same idea, right? The area under force versus distance is work. That's change in energy. You guys good? What else do I've got? Okay, so this is kind of the same idea backwards. you might see something like this, right? What if you have work in joules versus distance? Like you're transferring work, right? So as you push something for some distance, it's getting more and more work transferred. Right? If that's happening at a constant rate, that would represent a constant force. Right. Okay, so work equals force and distance. That looks like y equals mx all over again. You guys see slope could be force. That could be a little curveball graph that you might see, right? But you're definitely going to see force versus distance. Okay, right. So definitely going to see this one. All right. Unit 5, momentum. All right. So see, we've got conservation of momentum, inelastic, elastic collisions. Impulse is a transfer of momentum, change of momentum. Right. Some center of mass questions you might see. Yeah, you guys know you're looking for collisions, right? So if you see a collision, start already thinking in terms of momentum. So objects are colliding, right? Perfectly inelastic is they collide and stick, right? And always some kinetic energy converts to something else, right? Like waste heat, stuff that's hard to account for, right? You have to write that in a paragraph form, say maybe like waste heat and sound energy and like non-mechanical forms, right? That it's not MGH, it's not 1/2 m squared, it's right. If it's perfectly elastic, think Newton's cradle. So this right here, tick tock, tick tock. So perfectly bouncy. Right? Kinetic energy is conserved in addition to, of course, momentum being conserved. Okay. Okay. All right. And then what is this? The motion of the center mass of a system does not change due to an internal collision. Right. So this is if two blocks collide and they ask something about what does the center of mass do? How about this? If you watch two blocks collide, but you only focus on the center of mass of those two blocks, the center mass of the system, right? And you're watching it, right? But you're just focused on the center mass. Do you ever know when those blocks even collided? No, because before the collision, after collision, the center mass is always doing the exact same thing. The only way the center mass would change what it's doing is if there's an external force, right? But a collision between a two-block system is internal to that system, not external. Okay, right? Got that. Right. And you're going to get some question kind of like when it is raised, right? Something like that. AP likes that question. Right. Momentum is mass times velocity. Remember, this is a vector value. Conservation momentum. Momentum is conserved for collisions. Right. Oh, here's general conservation momentum. Right. All the mass times velocity bits add up. They equate. Right. These are for linear collisions, just in a straight line. Right. Which is all AP ever asks. Right. Here's perfectly inelastic. You guys know this one. They might have you guys. They might throw some numbers at you, right? But the mass of this block, initial velocities, boom, boom, right? What's the final velocity, right? You actually have to pull out a calculator and solve it. They like to turn this one into a math problem, right? So know that one, right? The perfectly inelastic, right? Notice I did not put perfectly elastic because math is really crazy, but if you get that and you have to solve it with numbers, then just test is kinetic energy conserved. Do all the 1/2 m squared bits before and after and say, does it equate? Okay. And then say impulse is a transfer of momentum. I should put equals delta P on here, right? So it's M delta V. That's also F delta T. Okay? There's the two perspectives on impulse, right? Right. So for example, you hit a ball with a bat. There was some force for some time interval. Maybe it's like a 200 Newton force for 1/10 of a second. That's going to take the mass of the ball. Suppose it's like baseball, it could be 0.15 kilograms. It's going to cause it to change its velocity, right? Oh, speaking of change of velocity, see if you guys remember this. What if the pitcher throws the ball to the left at 10 meters per second, and the batter hits it to the right at 20 meters per second? What was the change in velocity? 30. 30 meters per second. It's 20 minus -10, which is 30, right? Right? Okay, be ready for something like that. Don't worry about coefficient restitution. They're not going to ask that, right? Ooh, this one here. Two asteroids collide head-on perfectly inelastically, which means they stick, right? What's the final speed? Right, I'm going to cover this up. Right. So guys, look at those two asteroids. I got m times v going to the right, and to the left, I got half the mass at twice the speed. Ooh, so after they collide and stick together, what's their final speed? 0, because there's only ever 0 momentum in that system, right? Positive momentum, negative momentum, it exactly cancels out. They stick together, and they just stop dead in space, right? Get it? All right, what we got here? Ball hit by bat. Just mentioned that example. Given 4 of the 5 variables, find the last variable, right? So, because there's a whole bunch of questions that could be asked, right? Mass of the ball, initial velocity of the ball, final velocity of the ball, average force of collision, and the time of the collision, which again is probably like a tiny fraction of a second, right? Here you go. M times delta V is F times delta T. If you can identify 4 of those, you can solve for the fifth. Right? You guys do that? Right. And graphs. Oh, here's a graph. You're gonna see 2 days from now, probably multiple times, force versus time. And if you see that graph, I bet the question's gonna be, what was the impulse? And you can just find the area under that graph. Right? You guys see that? You might have to go the extra step of saying, what's the final velocity? Right? Then you kind of go back to kind of this ball and bat stuff, right? If you know the momentum transfer, you divide by the mass, they'll give you the change in velocity. You guys do that? Right? What is this one? Okay, this is kind of an oddball graph. What if you are transferring momentum with a force? So force times time, right? Here, I'm getting back up a little bit. So, and if you're watching the video at home, this is all a little tiny. But if you're watching this at class in front of me right now, I've got this zoomed into these 4 little cells right here, right? So these top 2 cells are energy. These bottom 2 cells are momentum. Reset. Got force versus distance, force versus time, right? And then my oddball graphs on the right are, see, energy transfer versus distance and momentum transfer versus time, right? And the slope of each of those represents a force, right? It's kind of like y equals mx, but right, okay, yeah. Force and distance, think energy. Force and time, think momentum, okay? If a rocket blasts its engines with some force for some distance, think in terms of kinetic energy. If a rocket is blasting its engines for some time, think in terms of momentum, okay? All right, you guys good? All right, so there's unit 5. Ooh, we are scooting through this. Unit 6, you guys ready? Unit 6. Unit 6, harmonic motion. Here's your main 2 categories of questions: pendulums and oscillating springs. Boom, boom. Right? There could be an oddball question apart from those, but that's the main 2 questions. Okay, right? So, here you go. Oscillating motion, pendulums, mass on a spring. You know to think in terms of unit 6. And here's your main 2 go-to formulas. Time period is 2 pi times square root L over G for a pendulum, or time period equals 2 pi square root M over K for a block on a spring. Those formulas are near the bottom of this page. They're right here. Okay, you guys remember right there? Okay. Boom, boom. You guys got those? Right, let's do this then. Six here. You guys remember time period and frequency are reciprocals? So for example, what if you are watching ripples on a pond and you see a leaf bounce up and down? It's like blip, 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 blip. Suppose that's like 3 blips per second. 3 blips per second. What's the frequency? 3 hertz. And what's the time period between blips? 1/3 of a second. Right? See how they go hand in hand? Like reciprocals. Right? All right. What's you got? All right, examples. A pendulum swing back and forth, given any 2 of the 3 variables. Okay, find the other. Right? So length of the pendulum, gravity field, time period of oscillation. Boom, boom, boom. Right? Notice what I did not include. Did I include the mass of the bob? Nope. Did I include the angle that you pull it from the vertical? Nope. If you get a free response question, just mention that maybe you want to keep it under 20 degrees. I've seen a AP award a point for that specifically. Say less than 20 degrees from the vertical, right? It's something, okay? So you guys got this one right here, basically, right? Oh, could you guys linearize that graph? Is that actually, that is an example coming up. So be ready to linearize something like this, right? So you got maybe different length pendulums. You're swinging back and forth, getting different time periods. Can you linearize that data? That's one of the examples I got coming up off screen right here. Okay. All right. What's my other example? A mass oscillating on a spring. Right. So mass of the bob, or say the block attached to the spring. What's the spring constant? How stiff is the spring? K newtons per meter. What's the time period of oscillation? Right? If you know any 2 of those, you can solve the third. Right? That's if there's some equation you have to solve. Right? And you guys know AP really likes graphs. Right? So here's linearized versions of both of those scenarios. So start with the pendulum here. Here's the pendulum on the left. Right? Suppose you have, here could be a story. Here could be a story. I think we did the story the other day. What if you land on an alien planet? Like you're like bounce around. I wonder what is the gravity field of this planet? What's the gravity field? So you pull out your physics pendulums, of course. And you got short pendulums, medium pendulums, long pendulums, try all different pendulums, and you let them swing back and forth, and you measure what's the time period. Right? So, okay, what am I going to do with this data? Now, you guys know if you had just one of those data points, you could solve the whole thing, right? But AP wants you to get lots of data points and linearize it, right? You guys get that? Because AP likes to do that, right? Here's one of many ways you could do it. in this example here, I set it up so that the slope happens to be exactly the gravity field, right? And how to get, so on the vertical, I put 2 pi quantity squared times L, and on the horizontal, T squared. Because you could start from, where is it? This one right here. I say, suppose I want to target G and I want that to make that the slope of my graph. Hopefully you guys can do this. Try to see if you can do this. I know we're going through this lecture style today, but usually last couple weeks I have you guys pull out your notes and see if you guys can do it too, right? So how could you linearize it to make this gravity field equal to the slope of a line, right? And this is the answer, right? So see if you can get to this same answer that you guys have this page too, because I gave it to you back in August and also like about a week ago. Okay, and then similar story for a block on a spring, right? So you got different springs and different, or no, sorry, scratch that. Suppose you have the same spring. You have one spring, and you have lots of different mass blocks, and you have a stopwatch. And you want to know, hey, I wonder how stiff is the spring? And you want to use this oscillation method. You do 2 pi quantity squared m on the vertical, time period squared and square seconds on the horizontal, and then you got lots of different data points, and the slope represents the spring constant. Okay, make sure you could figure that out yourself from scratch, right? Here's an oscillation graph. So like x versus t might possibly look like that, right? Oh, could be a sine graph, could be a cosine graph. Okay, you guys get that? Everybody good? All right, you guys ready for unit 7? Unit 7. All right, so we got here rotational dynamics, but also rotational kinematics. So rotational kinematic motion. I actually touched on that back when we were doing unit 3. So it broke up the turntable. You guys remember? Here's rotational kinematic formulas. Here's translating back and forth between linear and angular type motion, right? Say for a merry-go-round turntable. Right. Rotational inertia. You guys remember rotational inertia sticks? Right? Shift the masses around. It's harder or easier to shake it back and forth. Right? Torque, R cross F, results in I times alpha. Right? Rotational kinetic energy, angular momentum. Right? All those concepts. Right? We'll see here. Right, so see what else we got. Yeah, this row I didn't exactly follow my format for the table. Just kind of put as much information as if I could put here. Right. Here's some formulas though. So for a point mass, rotational inertia is mr squared. Right. If it's any other shape, then it's like the sum of that. So you could break a turntable into like a billion points and sum it up, and the net result is like 1/2 mr squared for a turntable. Right. Or for a solid sphere, it's 2/5 mr squared. You're not expected to memorize that. If AP wants you to calculate that, then they'll tell you rotational inertia for whatever shape, right? Parallel axis theorem, I'm not going to ask you about. Here you go. Torque is R cross F, which is R of sine theta, theta being the angle between those two vectors. Careful about that, because if they give you the angle from the perpendicular, that changes from sine to cosine, so watch for that, right? Torque is also got I times alpha. I should say net torque. Net torque is I times alpha, right? Because why would something accelerate angular if there's a net torque on it? Angular momentum is I times omega, right? Angular or rotational inertia times angular velocity, right? Analogous to momentum is mass and velocity, right? Angular impulse, right? So a transfer of angular momentum could be torque times time. That is analogous to impulse is force times time, right? Same idea, right? Same idea, right? I bet you're going to get a question that involves like a baseball being thrown at a swivel stick, and maybe it bounces, maybe it sticks and like rotates, right? And here, for a point mass, angular momentum is m times v times r, right? mvr, right? Where r is radial distance, right? That's really only true at a right angle, but AP always phrases it that way, so you can use that, right? Rotational kinetic energy, 1/2 I omega squared. Okay, you guys got all that? Right. Are we good? I've got 2 really good classic examples here. I mean, there's so many examples. So if I pick 2, then I'm picking 2 that I'm pretty sure you're going to see both of these. Okay, I think you're going to see both of these. Okay, so one is my classic. I wind a string. Guys, how many times have I said that phrase over the last few weeks? You wind a string around a turntable and you pull, right? You guys see? Here's like the forest for the trees picture of this. Right? You could go backwards or forwards with this. Is this force times this radial distance R cross F is going to provide some torque. That torque is going to cause us to have an angular acceleration, speed up spinning, or slow down if it's going the other way, or maybe it's frictional torque, something like that. So torque is R cross F. Torque is also I times alpha. Now you can solve for alpha. You guys get that? Right? And maybe you were told something like it starts from rest. Bam, you know omega naught. Maybe you're told you pull for like 3 seconds. Bam, you know time. That's 1, 2. There's 2 kinematic variables. Oh, and if you take this rotational dynamics and you solve for alpha, there's your third kinematic variable. Then you can go back to rotational kinematics, so you can solve for how far did it turn, how many rotations, or how fast is it rotating, omega final. Boom, boom, right? You see that? You've got rotational dynamics, torque, and also rotational kinematics, these 5 kinematic variables, right? Again, you could go back and forth on that. So they could tell you the force of the torque and ask for anything kinematic. They could give you a bunch of kinematic and say, hey, what torque or what force would have resulted in that, right? So you guys can go back and forth, right? Here's a seesaw. Maybe you want seesaw equilibrium. You guys remember the other example similar to this was a scaffold, right? So scaffold equilibrium, seesaw equilibrium, right? You guys remember this? Right. Given these weights, can you position these two people to zero it out? Right. So the torque would go to 0. Right. Also, the forces go to 0, but see, this pivot could be maybe pushing up. These guys are pushing down, right? But torque, R cross F has to 0 out. Okay, so there we go. So R cross F zeroes out. Let's get that. Right. Actually, probably a better question would be, what if you know the weight of one guy? Like one guy says, my weight is 100 pounds. Hey, what's your weight? They're like, I don't know. Hey, I see that seesaw over there? Here's what we're going to do. We're going to sit on the seesaw. We're going to slide you around until we reach equilibrium. We're going to solve for your weight. Right? Guys do that? Right? Right. Oh, ooh. These two graphs. You know you're going to get questions about these. Right? Torque versus time, angular momentum versus time. And both of these graphs might apply to the exact same story. Don't these go hand in hand? Apply a constant torque. Actually, this could be a story right here. String around a turntable. Pull that. So suppose you apply a constant torque for some time, you're increasing the angular momentum. That's an angular impulse. Okay. So in the graph on the right, it says angular momentum is increasing at a constant rate, where the slope is the torque. Yeah, these two graphs are opposite sides of the same coin, right? Same story, two different perspectives. Okay, answer that. We're good. Right. Right. So don't worry. Electricity, skip. Waves, skip. Right. Down at the bottom, real fast. We got about 30 seconds of class left. I know it. No, we have more than that. We got 2 minutes. Right. I got vectors and trigonometry and more reference. So let's look at these. So if you have vectors, that's something with a magnitude, but also a direction. Right? That's what distinguishes it from a scalar. Right. Here's a bunch of examples of vectors. Displacement as opposed to distance. Right? Velocity as opposed to speed. Acceleration, force, momentum, angular momentum, torque. All of those have some associated direction. And you could maybe use trigonometry to break these into components. Right? You guys can navigate around a right triangle. You guys do that? Here's Pythagorean theorem. Right? A squared plus b squared is c squared. Boom, you got that. B is c sine theta. A is c cosine theta. Boom, boom. Right? You guys know that? Hopefully you know that like the back of your hand by now. Yeah, you could also solve for angle given the sides. I don't think he's going to ask that, but you could, right? Could you do that? Okay. What's the? Oh, a ball is thrown at some speed at some angle above the horizontal. What's the initial vertical component of velocity? What's the horizontal component of velocity? You use trigonometry to figure that, right? Throw speed times sine of the angle, throw speed times cosine of the angle. Right? That'll get you started, and then the rest of that could play into a projectile question. Right? So it could be a little bit more to that. Right? Oh, a ball experiences a downward force of so many newtons and a horizontal force of so many newtons. What's the net force? That sounds like Pythagorean theorem, right? Something like that. You go back and forth that. Right. Add vectors to detail. So what if you have an object here? What if I have 4 different forces on this? I can push up to the right. I can push kind of down to the right. I can push mostly to the right up and maybe up to the left, right? All at the same time, right? So you can add those to detail and get what's the resultant, right? As if there was just a single force. You can add them together. Guys, can you add them together in any order? What if I start from here and I do this one first, and then this one, and then this one, and then this one? Do I get the exact same resultant? Yep. You can add, as long as they're all the same magnitude and the same angle, you can shuffle them around tip to tail in any order. They'll always give you the same resultant. You can add forces together in any order. Okay? Is that as if there's a single force on this object? Okay. Okay. And bottom row here. Here's base SI units. Here's prefixes. Here's basic graph shapes. Right? Guys, there's really only a handful of graph shapes that you see over and over and over in this class. Maybe a rare oddball graph, but it's pretty much going to be one of those. Okay, you guys got those? Okay. We got no relationship, linear, parabola, root, inverse. Boom. All right, that's the end of class right there. You guys have a good day, and we'll do one more day review tomorrow.